double integrals and volume over rectangles. If you have not watched the video on double integrals and area, I recommend that you go and watch that first. But now we're going to extend the idea of double integrals to find volumes. And when we say volume over rectangles, it means that we're going to integrate over a rectangle. So consider the region R, which is the rectangle, AB, and then XCD. This is not a cross product, it's just notation we use, which means all x's and y's such that x is between A and B and y is between C and D. So we have this region down here. And then consider a function z equals f of xy that is above that rectangle. Suppose we want to find the volume below the function, but over the rectangle R. And this idea can be extended to things where we get negative values, just like we got negative quote-unquote areas in single variable. So how will we do this? Well, this corresponds very well to what we did when we found areas. So the double integral over a region of dx dy or dy dx, we can change the order of integration, gives us the area. What if we multiply this by a third dimension? That is, what if we multiply this by a height? Well, in this case, we would now be finding volume. And how would we do this? So let's take this example here with our picture, and we're going to do the double integral of f of xy dy dx, so we're going to do y first, and then we're going to integrate with respect to x second, over our region R. So I imagine my picture right here of being really narrow skyscrapers, or really skinny rectangular prisms, whose base is dx times dy. So that's the base down here in the xy plane. And I'll call big B, so it's an area. A lot of people use big B for area. And then the height is the function height. And if I'm going to integrate with respect to y first, that means we're fixing an x value. So I did one x value. And then across the y's, we're going to add together dy times dx times height. So dy times dx times height. And then we're going to go to the next one and do the same thing. Multiply height times dy dx. Then the next one, height times dx dy. All the way till we get to the very end over here. We'll get to the very last one. And we add all of those volumes together. That is the volumes of those rectangular prisms. But then we go to the next x value, and we do it again. I'm not going to draw them, but I would draw these rectangular prisms at this first y, then the next y, then the next y, the next y, and we go all the way till we stop. And the inner integral says add that row of rectangular prisms together. And then we go to the next x one and repeat the process until we finish up, we get to the very last x. So the inner integral is summing this row of volumes. And then we do it again and again and again. And the outer integral says, now let's sum all the rows together. So there's the idea behind finding volumes using double integrals. The actual math of it is not too bad. Let's do a few examples. So let's evaluate the double integral 0 to 3, then 1 to 2 of x squared y dy dx. Now really, I should have said it the other way, because we're really integrating this first part here, the inner part. So when I have dy here, that means I'm going from y equals 1 to y equals 2 on the inner part. And I'll worry about the outer part in just a bit. So how do we integrate x squared y with respect to y? Well, just like with partial derivatives, we assume everything that's not a y is a constant. So I'm going to leave my outer integral 0 to 3, and then I'm going to integrate x squared y with respect to y, treating x as a constant. So we just get x squared times y squared over 2 from y equals 1 to y equals 2. Then we have a dx on the outside. Keeping the outer integral 0 to 3, and then x squared is like a constant. And then I'm going to plug in 2 for y, so we're going to get 2 squared over 2. Then I'm going to plug in 1 for y, minus 1 squared over 2. And we end up with this. So I'll rewrite this as the integral from 0 to 3 of 3/2 x squared dx. So the idea behind the algebra of double integrals, you basically just integrate twice. If you know how to integrate once, just your regular integration rules, it's the same idea. We have to do it 2 times. So now we're going to integrate this piece. The integral of 3/2 x squared with respect to x is going to be 1/2 x cubed from 0 to 3. Plug in the top limit. I like to factor out the constant, and we get 27 minus, plug in the lower limit, we get 0. And so the volume is 27 over 2. Take a look at our next example here. We want to integrate the integral from 1 to 2 of the integral from 0 to pi of y times sine of xy dy dx. So the order says we would integrate with respect to y first. Now, if I was to integrate with respect to y first, I would have to do this. And the technique would be integration by parts. If I'm integrating y times the sine of ky dy, that's integration by parts, which I know how to do. But what if we were to change the order of integration here? What if instead of integrating with respect to y first, we would integrate with respect to x first? So as is, remember, since the first one we integrated with respect to y first, it's y equals 0 to pi. And I drew the picture, that is, I drew the region over here on the right. And then the outer integral will be x equals 1 to 2. So we don't have to do a lot of work like we did in the video over areas to change the limits and try to figure out how they change. Because we're integrating over a rectangle, I can simply swap the numbers like that. Now, how does that help me? Well, let's integrate with respect to x. So I'll leave the outer integral there. If I'm integrating with respect to x, y is treated as a constant, so I just have y times the integral of sine of xy, which would be negative cosine of xy over y. Right? If I integrate the sine of kx dx, that's negative 1 over k cosine of kx. And then from 1 to 2. And put our dy. How does that help me? Well, I got rid of this y. Now I don't have to do an integration by parts, either on the first integral or the second integral. So we'll go ahead and plug in our limits from the first integration. So I have, remember I'm plugging this into x, so I'm going to have the negative cosine of 2x minus the negative cosine of, when I said x, I meant y. Let me fix that real quick. because I plugged in for x. Negative cosine of 2y minus the negative cosine of 1y, and then dy. Like that. And then we can integrate both of these pieces. So the integral negative cosine is negative sine, but this could be negative 1/2 sine 2y, and then plus the sine of y from 0 to pi. And if I plug in the top limit, I get 0. If I plug in the bottom limit, we get 0. And so the total integral, the total double integral, is 0. Now, a good question to ask is, how do you know when to switch the order of integration? And the horrible answer is, experience is going to tell you. Or if you try to integrate something and you just can't do it, your thought might be, let me switch the order of integration and see if it makes it easier for us. One final example here. Consider the region, which is a rectangle, x equals 0 to pi over 2, and then also y equals 0 to pi over 2. And we want to integrate sine x cosine y dA. So it's going to be the integral from 0 to pi over 2 because I have a rectangle, and 0 to pi over 2, doesn't matter which one I start with. Sine x cosine y. And I'm going to integrate with respect to y first because why not? As such. So let's integrate with respect to y. So I'm going to leave my x's alone. And I'm going to do sine of x is treated as a constant. And then we integrate cosine of y dy, which is a sine of y, from this 0 to this pi over 2, as if it mattered. And then dx. So the integral from 0 to pi over 2, and then sine x, just treat as a constant. And now we're going to plug in pi over 2 for y. So sine of pi over 2 is 1. Then we're going to plug in 0 for y. Sine of 0 is 0. And so we're going to integrate sine of x dx, which is going to be the negative cosine of x from 0 to pi over 2. Plug in the top, we get negative 0 minus negative cosine of 0 is 1. And we get the volume is 1. Now, a very quick side note. If you were to go back and look at this integral again, and I'll leave the limits off here, you might have noticed that I just did this, or I could have just done this. The double integral of these two things multiplied is the integral with respect to x times the integral with respect to y. I'd recommend going back and trying it to show that it actually does work. You know what? Let's go ahead and do that. I have a little time here. So I have negative cosine x from 0 to pi over 2 times sine of y from 0 to pi over 2. And if you look right above, we exactly did this. There's that part, and there's this part. And these two things are multiplied. Now, can we always do this? That is, can we always split a double integral into the product of two integrals? And the answer is no. Generally speaking, if we're doing the double integral of f of xy, where my function f of xy is some function of x only times some function of y only, we can multiply the two integrals like this. That is, we can separate them out. But if my function of y is, say, the product somehow of g and h, which are both also functions of x and y, then as a general rule, we cannot separate these two integrals and multiply them out. Just a little extra piece to think about when you're doing double integrals.